And so if I go cat.name, because it's still a positive class, I can actually see the name of that directory. And so what I want to do is I want to create for example, I want to create this delay mineral folder in the validation directory as well. So and then I can line is going to do is just going to create a directory validation folder with that class name. And we're going to do that for all of the directories in the training folder. And then we can then also list all of the images in that category, in that directory by doing this with So those are the current images in the training set, and we want to, this images variable contains all of the files in each of the directories, and we're just going to copy, because they're not ordered in a specific order, we can just try to copy, say the first, since there's 1,000 of them in each folder, we can let's say we want to make a validation set, then there's 10% of the training data set, we can copy the first 100 of those images to our validation set. And that we can, so we can make another for loop inside here for image in the first 100 images. Let's just see what that image then looks like.
Yes, they're making directories when they already exist.
You're right. Thank you. I'm just going to comment that out. So that specific file we would actually want to, it's currently in train, and we want to copy that into the validation set. So we're just going to say image.rename data valid cat.name cat.name and image.name. I'm just going to print this quickly and see if that's the right. That gives what I expected to give. Yeah. Okay. So we're going to run this for loop now. It's going to take the first 100 images of each of the two categories in the training set, and it's going to copy, it's going to move it to the validation set. And let's just remove. I'm going to run this, and hopefully it works, if it doesn't. actually go and look inside this validation folder and see if everything is there. So there we see all the new directories, and we can, so we want to see, look at the apple pie images. And there's 100 apple pie images now in the validation directory. Did I see a hand over there? Are you still with me? Is there anything you need to know that you...
Do you just use training and validation, or training and test? You do sometimes use training and validation and test, because of it, some people test the architecture first on the one, and then the final model results in the other one.
Yeah, so if I keep on evaluating a model on the validation set and then making decisions on that validation score, it's effectively training on the validation system also. So then the test set is there for that final evaluation after you chosen your model, and then to get an estimate of how it's going to do in real life. So after you scored your model on the test set, you don't actually want to change anything on the model again, because you don't want to specifically fit it to that test set. But for this use case, I'm only going to use a testing and a validation set because it's more simple. But if I keep on making adjustments after seeing the validation score, the end I will likely overfit a bit to the validation set, and I must know that it's a bit biased, the result, and it's not exactly representative of how it's going to do in real life. And for that I need to evaluate my model on the test set. Anything else? Okay, so all I did now, so now we have our data in our images in the right places. So we have a training folder, and we have a test and a validation folder. And in each of these folders we have a folder for each food category, and in each of these folders we have images of that specific food. So in Fast AI, you can create this data set class, and in this instance we're going to use the image classifier data from path function, and for that, if you look at the arguments, you'll need a path which we already specified. That is the path to the data. We need a batch size, so we can't load all of the images in our memory all at once. So that's why we have to create this generator object that feeds the images to the model at one batch at a time, or like where a batch is just a subset of the data, and we usually choose the batch set size of around 32 or 64, depending how big your memory is. And so that just means we're going to send 64 images to the model at once, and then it will clear it, delete it from the memory, and then load another 64 images and send it through the model. So that's what this batch size is. What's the batch size? Other thing we'll need is this transforms parameter, and this is basically telling the dataset class when you're reading the image what reprocessing should you do to this image before you give it to the model. And for now we're only going to do that basic preprocessing. So when we use a pre-trained model, we ideally want to use the same transformations on the image that the original model used when it was trained on the initial data set. So in Fast AI you have this transforms from model function, which you can specify the model that you're using, and it will automatically then get the transforms that model used when it was trained initially and store it into this transforms variable. And here we also need this, we need to tell it which model it is and what size we want the input to be. So let's choose the base model that we're going to use. And I'm going to go for the ResNet 34. So the ResNet is just a very popular and very popular convolutional neural network architecture that's proven over and over again that it's quite easy to train and gets very good results in a lot of computer vision applications. And the 34 just refers to the number of layers that it has. I'm choosing a smallish neural network just so that the training doesn't take too long in the session. So this ResNet 34 is also something that FastAI gives you, and we imported it when I in this line, and it already, when I call it now, it's going to download the pre-trained weights stored somewhere online, and I think it did that now. Okay, so it has, so this defines the model that we're going to use, the base model that we're going to use, and it has all the layers and all the weights for the layers stored inside here. So then we can give this to our transforms from model function. Let's put that before that. So we want the transforms that ResNet 34 used, and we also want, let's say we're only going to use a size of 256 by 256. So the image is 256 pixels. The height is 256 and the width is also 256 pixels. And we give that over here, I think, size. And we're not too interested in the rest there for now. So now you can see inside this transforms variable, we'll have the it will automatically gives the transforms for that we want to do to the training images, and so this is actually a tuple with the first element is the transforms that's being applied to the training images, and then the second element is the transforms we're going to do the validation images. In this case, they are the same except for this random cropping. Yeah.
We know it will be different.
It will be different when you'll see later when we're going to do some random data augmentations during training, and I'll explain why it's necessary a bit later. Then it actually, so what the data augmentations do during training is that it sort of augments the original picture just a bit, so it looks a little bit different than previous time the model saw it. So that artificially increases our training set. And when you're testing the model, i.e. when you're giving the validation images to the model, you don't want to apply those transformations, you actually want to see the original picture and not a transformed version of it. So that's why you have there's the two differences. But as you see, FastAI makes it very easy to, in fact, it does all that work for you, where in other cases you have to specifically say which transformations you want on both, on each. So we pass these transformations in this data assist class function. Let's see if there's anything else we're going to need. The default training name and validation name is the right names, corresponds to the directories that we already have. So this is just telling you the name of our training directory and the name of our validation directory. We don't have a test set at the moment, and this number of workers just says how many, I think, CPU workers just to train it in parallel or to load the images in parallel, and it's automatically set to 8. So we can run this. And now we have this dataset class, this FastAI dataset class, and in this dataset class we have the training data loader, and we have the validation data loader, and so these you can make an iterator of them, and then call them like you can call any Python iterator. and this will then produce a batch of images which we will call X and the corresponding labels which we will call Y. And this is also going to take a while since the first time we're running it. It might be a bit of a drive with some minute of AI, but hopefully that figure it out shortly. Not shortly. And we want to just inspect these variables, make sure it's in the right shape that we want it. So we would expect the X to be of shape 64 by 3 by 256 by 256, and that 64 is the batch size. The 3 is the number of color channels of that image, and the 256 by 256 is just the width and the height. And the Y, which is going to be our labels, our true labels for that data, is going to be represented as I think they give it as a set of integers. Yeah. So there's going to be 64 integers where each of the integers represent one of the classes. Let's look at Y, the first element of Y. So that's class number 60. So in this data set class that we just created, it also has this module called classes, so there we can actually see the classes of our data. And let's say we want to know what the 60 corresponds to. We can go Y, or let's just say 60. And so 60 is the lobster category. So this was just to check that our data is being imported in the right way and processed in the right way. If we actually want to plot, let's try and visualize one of the images in this X variable. Let's say the first one. Okay, so the plotting library we'll actually want this in a different format. We want it by 256 by 256 by 3. So we need to reshape that format. Now I don't want to get stuck over here. So this part we can also do with the validation data later, but I'm not going to do it now. In this data set class is all that we need to get the data into the right format before sending it to the learner, to this learner class. And so actually now we have all we need to create this learner class, because we have our base model, which we set with the ResNet34, and we have our data object. And what this does, there's downloading the pre-trained weights. So what this did was to get the ResNet34 architecture, download its weights that it got from training on ImageNet, and it cut off that final output layer of the original ResNet34 and replace that with a layer that a fully connected layer that will produce the food category. So 101. So it has 101 output neurons, and that's the part we're going to train. So that's the part we're going to train. We're going to leave the rest of the model we're going to do fixed. So to train this learner, all we have to do is call this fit function, And the split function wants to know the learning rate, and it wants to know how long you want to train it for. So at the moment, I'm just going to choose a small learning rate, or a constant arbitrary learning rate, and I'm going to, let's say we want to train it for 2 rounds. So that means every image is going to be passed to the model. So it's going to, it's going to send all the images per batch to the model, and then when that's done, it's going to repeat that process again. And this is also just a random number that I chose just to show you how the training is going to look like now. And it's going to start in a while. Any comments so far? Does this look easy to you? Do you think is it difficult to follow? Do you know better ways of doing it?
Can you zoom in a bit?
Sorry. Is that better?
Yeah.
Sorry, if you didn't have the resonate architecture, would you then just play around with different numbers of hidden layers and different numbers of nodes?
So for most, I think for all of the computer vision problems I've worked on, it was never necessary to create my own convolutional neural network architecture, because people spend a lot of time. Thank you. People spend a lot of time designing these architectures and training them on bigger data sets, and I don't want to recreate the wheel every time I do a project. So I trust that they know what they're doing, and I build on their work. So if you design your own network, then you'll have to actually need the resources to go and train that network on a larger data set. So you do this pre-training as well. And yeah, so for most of the use cases, the point is that using the existing network is going to be sufficient. But if you really want to do it, there's another way you can call this and actually specify the layers or the architecture that you want to use. And I'll give an example a bit later as a demo where I didn't create the model from scratch, and I also didn't design the model myself. It's someone else's PyTorch code, which I used that PyTorch definition of that model and gave that to Fast AI, and it wrapped it in this trust. But yeah, so actually, yeah, is that good? So here you can see the model is training, and it's taking around 5 minutes per round, or what they call it the epoch. And so each iteration is importing 64 of those images, transforming those images in the way we told it to, and then sending it through the network, getting the predictions for those 64 images, comparing those predictions with the actual values, so the true categories, and then evaluating how well it's doing, and then we're going back to the model and adjusting the parameters so that we'll get better outputs in the next round. And here it's reporting the loss, and this is the loss on the training data, but we're more interested in loss in validation data, which it will output after each epoch of training. So as you can see, if we filter this code a bit, the actual amount of code that we need to do this. So if we forget about the data moving the images around, the only code we actually need to fit the model, create the model and fit the model is how many are there are 7 lines of code to do all of this. So it's really not complicated at all to get started with this. Obviously it's going to take a bit of time to understand what each of these things are doing, but it's not a lot of code where in the past you will have pages and pages full of code just to create something like this. And so there one epoch was finished, and the training loss is 2.1 and the validation is 1.6. And this is the validation accuracy of 57%, which is not great, but it's the first epoch, so hopefully we can get it a bit better later on. And also this is just a very basic model. There are no bells and whistles here. It's just it shows a random burning rate and just a random number of epochs and nothing else. And this is only fine tuning the last layer of the network.
Do you think?
Oh, sorry.
Will it automatically train on the GPU?
Yes.
Faster, okay.
Yeah. So we'll have this. I think we can use torch.cuda is available. I'll see now once this is finished. You can actually check if it's seeing the GPU. But yeah, so fast AI makes that very automatic. I didn't have to do anything, and it's training on the GPU now. And fast AI also has the CPU version where when you go to the fast AI GitHub repo, and here's the installation instructions. So you just clone this project and you go in there, you do that update, and yeah, that's all you need to do. And yeah, that gives the instructions for the CPU and the environment. So when you don't have the GPU, but it's not recommended to train a convolutional neural network without GPU.
So tell me, this salamander, I think it's per hour that you pay, eh?
Yes.
So for someone new in this environment, would you suggest maybe try to get it compiled, let's say offline, until you can utilize? Because at this point, most of my cost would be just to get out.
Yeah, so that's a good point. So there are cheaper servers, which is, the cheapest one is this with only a CPU, so it's $20 and I think it's probably not that easy to upgrade the server. So yeah, you would actually want to write the code, like write this code and see if everything works. If you really don't want to waste money, then you can write this code and check if everything works, and you can train it maybe on a sample of the data and not all 100,000 we have now.
So the end you want to pay for the power you utilize and not staying internal.
Yeah. So once you have this notebook or the script that you want to run, then you can upload it to this server. But what Peter just showed me is there are actually compute environments that you can use that are entirely free. One is the Google Colab. So Google Colab, I speak on a correction because I looked at it a while ago, but I think it has an 8 gigabyte GPU.
Yeah, it's got
and 16 gigabytes of RAM.
and 4-core CPU.
Yeah.
For instance.
And it's also like this notebook environment, but I'm not. The last time I used it wasn't that easy to get my own data in there, download other packages that I wanted to use, and I can't store. I couldn't store my environment and log up and log back on again. I had to reinstall everything again. But maybe I was doing something wrong. Maybe they've improved on that now. So it's worth your time to go and check that out. Google Colab, and the other one is Kaggle kernels. And Kaggle kernels also recently added GPU services to their compute environment. And I think, so there you have access to all of the Kaggle data sets, which is quite cool, so you don't have to move to download that from external places. You can just, you have access to that, and you can actually store your notebooks. And I think that most of machine learning and deep learning libraries already installed for you in the kernel environment, so you don't have to worry about that. I think it's just not as fast as it would have been with the service like a dedicated service like this, where you have a full functionality of a full machine. There you only have this notebook environment. And I think it's also being shared, the machines are being shared among all the people using it, and then according to the supply, your speed might be throttled. So our model is done training for 2 epochs, and you can still see our validation loss is a lot lower than our training loss, which means we can actually train it for a bit longer at least to see what it's doing, and we're at 60% accuracy at the moment. Let's see if this is the right. So there, I checked it. This just checks if the GPU is available. So to get the actual predictions using this model on the validation statement, you can just call learner.predict, and this will automatically send all the validation images through the model and get their prediction. And these predictions will now be in the shape of will be an array or a matrix with the size of the number of validation images by the number of categories in our data set. And that is because for each image we'll have a score for each of the food categories, and each of those scores will represent the model's confidence that that is the right label for the image. So we can actually look at the shape, make sure it's right, and there we go. We've got 10,100 validation images and 101 categories. We can look at the first row. So to get the actually the way this model was defined is that we first need to take the exponential of these values to get it in the 0 to 1 range that we want it in, so that they represent, they don't do exactly, but so that they can mimic probability scores. So you can better interpret this. A value close to 0 would mean it's unlikely that this image is that category, and a value close to 1 would mean it's highly likely that this is the category for that input image. So to get the actual label for a single image from these scores, we can get the max for each row of these. Let's call these plots. So to get the actual prediction, we can go to all max. So this is now an array of shape 10,100. And each of these integers represent the prediction for the corresponding input image coded in this integer format. So when I see the actual classes, you can go So the prediction, the actual labels predicted for all of the images in the validation set. So a good idea would then normally be to go and inspect the results. So actually see where so in this data set class we can access the validation labels with this. And we can then compare these labels with the predicted labels and see where they're not the same. So these are the indices of the input images that were incorrectly predicted, and we can then actually go and look at the file names the files that were incorrectly predicted. Look at the first image that was incorrectly predicted. Go and check what was actually, can see what the actual label is versus what was predicted. But yeah, I don't want to do that now because we're running out of time. But the thing is, it's a good idea to actually go and visually inspect your outputs and trying to find, see which images it's getting wrong, and trying to maybe we see it. All of the images of the hot dogs is not predicting right, then it might be a good idea to get some more images of hot dogs, or to get, or maybe you should make some architectural change or whatever. But the point is, it's good to actually compare your results with the input, or to visually inspect it. So this was a very basic model that we trained. And there are still a lot of things we can do to improve on this. The first thing I would have done here is train it for at least 5-6 more epochs, because we can actually go and inspect the loss. The loss is still steadily decreasing, and if we train it for a lot longer and it continues decreasing like this, we can probably get a nice score. But besides that, we can, here we just chose a random learning rate, where there are lots of learning rate schedule. So this is just a let me first say what a learning rate does. The learning rate controls the rate at which the model learns, and so that is the steps we take after every iteration, the size of the step we take after every iteration when tuning the parameters of the model. So if we take too large steps, we can get to the optimal solution quicker, but we also might overstep the optimal solution when the learning rate is too big. So then we'll want the smaller step size learning rate, so that we don't overshoot the best solution. But then the danger is that it takes very long to get to that optimal solution. So there are lots of things that people suggest to to improve. So this is also just a constant learning rate. So through the whole training process, we just kept the learning rate at 0.01. But people have suggested in using starting small and going with bigger, or starting at a certain rate and after a while decrease the learning rate a bit, and next round decrease it a little bit. Some people have suggested doing like these cyclical learning rates, and these are all just experiments that people recommend, or the experiments that people are doing to see if there's a better way of getting to an optimal solution in this fast space. Excuse me. Quicker and in a more robust way, not getting stuck in this local optima or minimum. But in this, so the best way I've seen of scheduling your learning rate is called, firstly, in choosing a learning rate, so where to start. The Fast AI library has something called learning initialize the model, so create a new learner. Fast AI has this built-in function called learning rate finder. So what this does is training the model, but after every iteration it's decreasing the learning rate just a little bit, and then thereafter we can, when it's done doing that, we can plot the learning rate against the loss, and we'll typically give a curve like this, and then, so actually I don't, so this is a bit of a theoretical part, but if you want to research it further, you can go to this one cycle. The guy wrote the blog post on this policy. So this is, when you do the learning rate finder, you'll get something like this, a curve like this, and then they suggest, and I'm not going to go into the detail now why, but they suggest of using the learning rate just before the local minimum was reached. So here they would suggest a learning rate of 10 to the power of minus 2, the 0.01. And so that's what we're going to do. And here, this is the learning schedule that this guy suggests we should use, the learning rate scheduler that we should use. He didn't invent this, he's the guy who wrote it into Fast AI. The guy who did the main part of the research for this work is called Leslie Smith, and I think he wrote a few papers on how to optimally train your neural network, and he found this phenomenon called superconvergence, and he says if you choose your learning rate in this fashion and start small with your learning rate and then linearly increasing it, and after a while start decreasing it again, it's the best way of finding a good solution. But unfortunately that's all I can say about it now. But the good thing is that it's already implemented into the Fast AI library, so it makes it very easy to train it in this fashion. So after that first part, we'll want to see the loss. We'll want to find the learning rate then. parameters that we set for this one cycle policy. We're just saying start, let the max of that schedule be 10 times of the minimum, and the last 10 iterations decrease it at a slower rate, which is this pink over here. Last 10%. But the details doesn't matter. I just want to show you that this can be done in fast AI in a very easy way. And the last thing we're going to try and implement now, or add to now, to try and improve our model, is to use data augmentation that Peter was referring to, or that I was referring to when we were discussing these transforms. So what we can do with data augmentation is that instead of every time we show an image to the model, instead of showing it in exactly the same way, we can do some random transformation on an image without it losing its actual semantic or its meaning, but it's still being displayed in a different way. So, for instance, making a horizontal flip of the image, or rotating the image a bit, or adding some pixel noise to it. If I so for instance I flip a hot dog, the image of a hot dog, we'll still be able to see that it's a hot dog, so it still makes sense to be labeled as a hot dog. But this helps a lot for the model to not overfit to those exact images in our training set. And so in essence it's actually increasing our training data size. So this we do, where are we now? So this we do when we call our data set class, we call it image specify data now. Compile again, let's just copy this code. And now our transforms, we're still going to use this transforms from model function. And we're still using our base model, and we're still using the same size. But you see there's an argument for augmented transform, and that's where we're going to specify the additional random augmentations that we want to do to the images before sending it to the model. And very conveniently, Fast AI already has this set of transforms that we can use for images like this. I think it's called transform site on. So this is a set of transforms we can randomly rotate, we can randomly do some lighting, add some pixel noise to the images, and we can randomly flip the image before feeding to the model. So we just add that in here. So now this is transform object exactly the same as last time, but with these additional augmentations, and now we can actually compare the transform object from the training data to the one in the validation. For the validation data, and then we see it's a bit different. The random rotate and the random flip and the random lighting is not in the validation version of this transformed object, because when we actually want to predict, we don't want to apply those transformations to the images. So now we can create this new data set class with those transformations. And we already found the best learning rate for our use case, and we can now fit it using the one cycle policy and see how much better it does. So I actually want to, while this is training, because you see it's going to take a while, 3 minutes, so after 15 minutes we've done training. So while this is training, I want to show you the stuff we did yesterday. And there we actually actually just built, or I built a hot dog, not hot dog classifier. But I did the notebook beforehand, and I just scrolled down and described everyone what I was doing. And then when I trained it in exactly the same way as this, except it was just a binary classification problem instead of this multi-class classification problem. And yeah, but everything else was done in the exact same way. We just added, so the images was split in the same way, but the directories were just hot dog and not hot dog instead of hot dog, apple pie, whatever. So I trained the model and I saved the model and I downloaded the model to my local piece, to this laptop. And here I wrote a little function, just what it does, so it's this one. What it does is just imports the model over here.
Sorry, can you just zoom in a bit?
Sorry with that. Is that better?
Yeah, thanks.
So we're just specifying the size here, loading the model, again using that transforms, determining the transforms, and then I'm using OpenCV to capture the images from my webcam. So it's reading in the image frame, right frame from my webcam, and I'm just converting it into the right format to correspond with FastAI. Here, so this is the image in the RGB format. So this is then being put through the validation transforms. That part I'm not going to discuss now. I'm just telling it this, just also to put it in a format for to read. And all of these things I'm doing here is what's being done automatically in FastAI, but I'm not using FastAI in the same way here because I don't have GPU access. And here I'm putting the processed image through the model, and I'm getting the probability scores. And then if the score is greater than 0.5, it's a not auto. That's just the way we set it up. If it's less than 0.5, it's going to be auto. And that's just plotting the label on top of the image. So I'm going to show you how hopefully this works now. How do I see this time? I'm in the right place. So it's going to run a bit slow on here because it's running on a CPU and not a GPU. So correctly, yeah, see, so there's still a bit of mistakes, and the data set we were using is not the same as the one we're using now. It was actually, I think it's thinking my fingers are So yeah, I keep talking. So the data set we were using was actually very dirty and like things that weren't there were lots of noise in the labels. So when we actually tried to inspect why our model is not doing that well, we saw that in the training data there were some images that were labeled as hot dogs which weren't really hot dogs, and also, so that's probably a reason why it's not doing that well over here also. And I think it's also, if I move quickly and do like blurs, then the model gets confused. I'm going to search for a hot dog image on my phone and see if it picks that up. So I'm going to show this picture of hot dog to the camera and see if it, so it's actually
sorry, will it only look at a certain part of the camera's view or the whole image?
I think actually at the moment it's only looking at the middle part of the image, but we can change that. That's just so what you actually can do in practice is to take if your input image is a bit bigger than the one you trained on, you can actually do like the sliding window approach where you take like these corner crops and evaluate the model on the four corners and in the center of the image to be predicted, and then you average those scores to get a final output, just to make sure that you're covering everything. And that's also like a variance reduction method. But so the part we're not going to see how the training is going. Okay, that's not at the moment. So I think we can actually get around low 80s, maybe high 80% accuracy just doing this and training it for a bit longer. If we're going to do it, so I'm not going to waste your time and get to watch paint dry all day. But if you carry on like this, training it for say 10 rounds, I think the accuracy will be a bit higher than this. And I quickly searched the internet to see what people get on this data set, and I couldn't find anyone that got more than 82%. So if you try this at home and you get around that mark, you'll know that you're doing the right thing. But I'm very confident that doing it this way, which I haven't actually done for longer than this, will get you around that mark. So the other thing that I also showed yesterday, but didn't go into detail about to do it, is the task of segmentation. So that's where I was using this data set called this data set constructed by Microsoft, and you can explore it over here. And I think there's 120 images, 120,000 images. So when I look at it for humans, so this is what a picture, one of the example pictures are in this data set, and it actually has these polygons drawn over relevant parts of the image, so we can look at all the people in this image, and that's exactly what I used in the next. So this is a segmentation problem, so a person segmentation, and there were actually 60,000 images of these where there were actually people in it with these polygons drawn around them. So that was sufficient for training a model to actually learn how to do that. So now instead, where your output was a vector of size, the same number of classes that you have, the output is now another image, or a matrix rather, where the matrix is the same size as your input image, but now instead of where each cell in that matrix represents the probability or the score given by the model that corresponding pixel is a pixel of a human or not. But that's the only change that you make to the model. And when I train the model, so actually the reason why I trained the model like this is because I wanted to replicate anyone who watches what's a series called Black Mirror. Have you watched the White Christmas episode where the people get blocked? I'll show you now.
You're free to go now, Trent.
So this guy did something wrong, and now as his punishment, they have these things in the eyes that filter the image, the things that they see. So now, so his punishment is that he can't, every person around him is now blocked. And so when he sees them, you'll see now everything is blurred, and he also can't hear what the person is saying. And the same way, other way around.
You're not register.
What does it mean, this register?
It means you're blocked
By who?
by everyone.
knows what a human looks like, we can highlight, or yeah, we can just eliminate everything that's not a human in the back. So there you don't need a green screen behind you to actually, so we can implant other photos in the background. Maybe this can be used when doing writing or when recording videos. So let's see how well the model is doing. So you can see it's learning slowly, but it keeps on improving, and there's still a large gap between the training loss and the validation loss, meaning it's doing better on images it hasn't seen before during training. So here I would suggest that we might want to use a larger network, so maybe a ResNet 50, and so the larger networks have more capacity to learn, but it's also harder to train. So if you have little data, you might overfit, or other things can go wrong. And then the processing time is also going to take a bit longer. But the other thing, so at the moment we're only fine-tuning the last layer of this network, and keeping all of the other parameters of the layer of that network fixed. But by using this command, or learn.freeze, we can actually make the rest of the layers also trainable. So learner. We can make the rest of the layers trainable, and there we'll just use we will use smaller learning rates for the lower layers, and a bit bigger learning rate for the middle, and then the largest learning rate for the final layers. And the idea there is that we don't want to, this one makes sense now, but yeah, so I don't want to go into that now, because there's some background we need for to understand that. But the thing is, so then we can just fine-tune the rest of the model to fit our data, and it will also result in some improvements, and it will fit it in the same way as we've done over here. It's just now then the training will be tuning the rest of the layers and not only the last layer. Other things we can do, which I didn't prepare a notebook for, but which I experimented with when deciding on what to show you, was object detection. And in object detection, the task is to draw bounding blocks over things of interest. And here I trained it on a data set with vehicles in it, and with bounding boxes around vehicles, and then also the label of that thing inside of that box. So there your output would be, instead of labels, or instead of a mask, a segmentation mask, that it would be the coordinates of the bounding box, and then the corresponding score for the type of vehicle in that box. And that can also easily be done using the fast AI library, and we get pretty good results doing it like that. But that's what it